Hi, in this video we will see how to calculate the flux of the vector field across the open surface in the form of cylinder. So we have a vector E and we have an open surface in the form of cylinder with radius r and height h. What is open surface? It's like a sheet of paper which we close up to form a cylinder. Its cylinder is open. It means that we can go inside and we can go out. So it's an open surface. Now, as you can see that the open surface, for the open surface, we can add a unit normal vector to the surface in two directions. The first direction is outside of cylinder. It's like this, and another direction is inside the cylinder. And you remember that for the open surface we have two possibilities to calculate the flux. So we need this normal vector, and we have two possibilities. To normal vector directed outside the cylinder with unit vector ER, radial unit vector, and inside. So I will choose a normal vector directed outside. The second step, I will find a test area ds, and for the cylinder I will calculate this test area in cylindrical coordinates. So it will be r d theta times dz. And now, to calculate that flux, I need to define a unit vector, and as we've discussed, I will take the direction outside of the cylinder. So the E vector, the field vector, goes, for example, out from this surface, and the flux across this test area will be unit vector times ds dot product E. Thus, we need to calculate the dot product. Firstly, I will define my unit vector, and it is ER in cylindrical coordinate. However, vector E is expressed in Cartesian coordinates. In order to calculate a dot product, the very important step is to express the both vectors in the same coordinate system. And the easiest way, taking into account that E is already expressed in Cartesian coordinates, I will express ER as a function of EX and EY in the Cartesian coordinate system. So we have two vectors of Cartesian system, ERX and EY. And I will add to the drawing my unit vector ER for the polar coordinate system and the angle theta. Now I can express my ER vector as a function of EX and EY. So I will do the projection of the ER vector on the x-axis and on the y-axis. So theta angle also here, and two projections ER equal the magnitude of ER, it's a unit vector, so the magnitude is 1 times cosinus theta times EX plus the magnitude of ER sinus theta times EY. The magnitude of the unit vector are equal to 1, and I can express my unit vector radii in the polar system as a function of the Cartesian vectors. So, three components: cosinus theta, sinus theta, and 0. And I have my E vector in the Cartesian coordinate system, expressed in Cartesian coordinate system, with three components: x plus that, y plus that, and that. And now I can calculate a dot product. My two vectors are expressed in the same coordinate system. So the first component is cosinus theta times x plus z plus sinus theta times y plus z plus 0. Thus, I will rewrite my d phi, a flux across this test area. It will be the surface of this test area expressed in cylindrical coordinate system, r d theta dz, times a dot product. And now, as I can see, I need to integrate as a function of theta and z. And my x and y of Cartesian coordinates can be expressed as a function of theta and r. They are function of theta. So I need to, if I want to integrate, I need to express them as a function of theta. And I know that in polar system, x can be written as a function of r a theta as r times cosinus theta, and y can be written as r times sinus theta. And now I will replace x and y in the phi expression. So I will have r d theta dz cosinus theta times r cos theta plus z plus, I will continue here, sinus theta, r sinus theta plus z. I will rewrite r d theta dz, r cosinus square plus z times cosinus plus r sinus square plus z times sinus. Well, here I have two terms, r times cosinus square and r times sinus square. Cosinus square plus sinus square equal to 1, so I can rewrite r dr dz, r cosinus square plus r sinus square is equal to 1, thus I will obtain r, plus z, and here I will rewrite z times cosinus plus sinus. So I have two variables, theta and d, and now I need to calculate the total flux. I need to integrate as a function of theta and z. And in the cylindrical coordinate system, here for our cylinder, theta and d are independent variables. Thus, I can separate two integrals, and I can calculate separately the integrals related to theta and the integral related to z. So the first integral I will rewrite r square d theta, and theta varies from 0 to 2p, integral times integral dz, and z varies from 0 to h. Another term I will obtain, so r, and I will put together all the terms with theta. Thus, it will be cos theta plus sinus theta d theta times, now the term concerning z dz, 0h. And I can do it only in that case where the two variables are independent. For example, when I fix z, my theta for any value of z varies from 0 to 2p. So now I will calculate my integral. I will obtain 2p times h times r square plus another integral r times z sinus theta plus minus cosinus theta, and I need to apply so theta 0 and 2p, and I will obtain as a result 2p h r square. Indeed, sinus of 2p equals 0, sinus of 0 equals 0, cosinus of 2p equals 1, minus cosinus of 0 equal 1. So cosinus for this term I will obtain 0. Cosinus of 2p 1 minus 1 equals 0. So the total flux will be equal to 2phr square. The flux is not 0 across this open